are now ready for chapter 8. We're going to do this just like chapter 7, so we're only covering a couple sections. So you've got your notes packet, that's for today and tomorrow. And then I'll give you the assignment packet today that has both pieces. And then I would like to take a quiz on Friday over chapters 7 and 8. So we will do a little review. Yesterday we reviewed chapter 7, so the normal stuff, and that's going okay, I think. It seemed like we were doing pretty well with it yesterday. So in chapter 8, we are still talking about some distributions, but this one is looking at distributions of the sample mean. Okay, and to kind of explain what that means, I have a little scenario here. So if I want to find the average household income in the United States, and I take a survey of 10,000 households, would the mean of that sample be the same mean as the total population? No. Okay, we know that a sample is hopefully close to the population, but probably not exact. Okay, if I take a different 10,000 households, would I get the same mean as I got in the first time? No, probably not. So we are looking at a distribution of all the different sample means. So if I were to take a bunch of samples of 10,000 households and look at the means of all of those samples, that's the type of distribution we're talking about. So I kind of have that definition there. So the sampling distribution has all the different possible values of that statistic. In this case, we're talking about the mean for a given size. So the sampling distribution of the sample mean, so for X bar, is the probability distribution. So we know probability distribution has like your possible outcomes and the probability of each for all those different samples. So to make a little more sense, we are going to look at a concrete example where we could actually create our sampling distribution. So let's say, very fitting since it's Halloween, we're talking about pumpkins. The population is the weight of 6 pumpkins in pounds displayed in a carnival guess the weight game booth. You are asked to guess the average weight of the 6 pumpkins by taking a random sample without replacement from the population. What does it mean when I say without replacement? Yeah, I can't pick the same pumpkin twice. I have to take 2 different pumpkins. And I'm going to use the average weight of those 2 pumpkins to guess the average weight of the entire population. All right, so can I find the true mean of this so I know what the right answer is? All right, how do we find that out? Add them all up, and we would have to divide by 6 for the 6 pumpkins. $84 divided by 6. 14. So the true average is 14 pounds. So if I want a sampling distribution of the sample mean for a sample size of 2. So that is listing every possible outcome for that. So I have to first think about every possible combination if I take 2 pumpkins. And I've kind of started a table here for you. We're just going to kind of fill it in. So I could take A and B, A and C, A and D, A and E, A and F. Okay, those are all the combinations involved in pumpkin A. B and C, B and D, B and E, B and F. C, D, C, E, C, F, D, E. What am I missing? Which 2 combinations have I not already included? D and F. And the final one, E and F. Okay. So that's every possible combination. So then we have to look at the sample means. So you have to take the weight of those pumpkins, add them up, divide. That's how I got my Y bar. So I did a few of them for you. A and E. So pumpkin A weighed 19 pounds. Pumpkin E weighed 10 pounds. So add those up, divide by 2, and that average would be 14.45. and F. So pumpkin A is 19, pumpkin F is 17, so the average there would be 15. So I did those B and E. So pumpkin B is 14, pumpkin E is 10. So that averages B and F up to 14 and a 17. 15.5. C and F, so pumpkin C weighs 15 pounds, pumpkin F weighs 17 pounds, we get 16. D and F, so pumpkin D is 9, pumpkin F is 17. So 13. E and F 10, and 17, so 7, 5, 2, 15. Alright. Does everyone know where I got those sample means from? Alright, so the probability of each of these. How many different groups do I have here? 15. So the probability of each of these given groups would have been 1 out of 15, right? So I'm not going to write that 15 times. Just the same all the way through. So any combination of pumpkins that I choose, there's a 1 in 15 chance that I chose those two pumpkins and got that weight for my sample mean. Okay, so the actual probability distribution doesn't even have all that information. It just has the sample means and then the probability of each of those. So we look 9.5, I put them in increasing order here. So how many times do we get 9.5 as a weight? 1. So there is a 1 in 15 chance of that. 11.5, we got that 1 time. So there is a 1 in 15 chance of that. 12. Yeah, 12 came up twice. So the probability of getting a sample weight of 12 is 2 in 15. All right, sample weight of 12.5. How many times did that come up? Okay, how many times do we get 13? 13.5? 14? 14.5?
2.
And the rest of them, I think, were just ones. So the actual distribution lists every possible outcome, which it was the mean, and the number of times we got it for our probability. So far, so good? So then, what's the probability the sample mean is the same as the population mean? What's the probability that I take my 2 pumpkins and I get the correct weight? Yeah, the true weight, we already found that the actual average was 14 pounds. So there is only a 1 in 15 chance that I would guess the correct average weight from my 2 pumpkins. You guys okay with that? Okay, so here's another question. What is the mean of the sample mean? Probably easiest to do it from this screen. Here were all of my means. So if I want to find the average of those means, what do I do? I'll add all of those and divide by 15. Let's see what we get.
Do you have a new calculator? This is nice.
What's it engraved on the back? What year does it say?
23.
More than my new one, sure.
23 too?
Try to get a couple new ones every year.
17 too.
Replace them as they
It's
die.
even hard to click in.
This is an aged calculator right here.
This is like a fine line.
So, it averaged, what'd you get? 14. Haven't we seen that before?
Yeah.
Yeah, that was the same as the actual mean. Okay, well maybe that was just because we were lucky. Let's see if that works again. So, we're going to stay with this example because it's concrete. We can look at all the possibilities. It's easier to think about. I want to do the same thing, but this time I'm going to allow you to take 5 of the 6 pumpkins for your sample. So basically, you have to leave out 1 pumpkin each time. So I've listed some of the options. So first option, you could leave out pumpkin F. Second, leave out pumpkin E. Leave out pumpkin D. Leave out pumpkin C. So we need the option without B. And then the option without A. Okay, and so then to find the average, we take all of those weights and add those up and divide by 5. I wrote down the wrong thing here. Don't do what I wrote down. I wrote down the wrong weight. Let's see. Okay, left up. So we have 19, 15, 16, 10, and 17. I think I wrote down all of them instead. Alright, so this one we get 14. And without these. Okay. So what's the probability of getting each of these weights? 1 out of 6. There's only 6 combinations here. So the probability of selecting each of those groups of pumpkins is just 1 out of 6. Alright, so let's see. What's the mean of those sample means? So if I want the average, we have to add up all my Y bars. We're dividing by 6, and we get 14, the same as before. Alright, so do we feel confident that the average for the sample means would be the same as the original? Okay, let's talk about the error in these. So error, that's kind of like standard deviation, except I don't really want to calculate it for all of those. Let's just kind of look at how spread out our data is. I'm going to do a very informal thing here. So I'm just going to kind of look at a graph. So I'm going to plot my means here for each group. So the first one, we had those 15 means. So I'm just going to put dots. So we had a 16.5, 17. Do you guys know what I'm plotting here? The Y bars, sample mean. So we got from the first one. So I got 14.5 twice. I'm just going to stack them. Just putting dots to represent each mean that we found in that first sample. So I can see that first one was pretty spread out. And then I'm going to do the same thing with my sample of 5 pumpkins. Alright, so I'm trying to compare the error. So the original, those black ones, are when my N was 2, when we took a sample of 2 pumpkins. My purple ones are when my N was 5. I had a sample of 5 pumpkins. So what would you say? How would you compare? What could we say about this? When the N was 5, there was less spread. The probability of getting the actual mean was, what was the probability of getting 14? 1 in 6 versus with the other one we got 1 in 15. So what we're seeing is when our sample is bigger, our data is less spread out. It's more consistent. It is closer to the average, which shouldn't that make sense? If you take 5 pumpkins, wouldn't it be a more accurate average than only taking 2? Yeah. So the bigger your sample, the closer, the more likely you are to get something that resembles the true population. All right, so what role does N play? A larger N would give us a smaller standard deviation, the spread, so a smaller standard deviation. So we like large samples. Our data is more accurate in that case. So all of this was just kind of our background so we can kind of understand what a sampling distribution of the sample means is, because that just sounds confusing to say. But the big things that we need to know, the mean for the sample means is the same as the population mean. The standard deviation for the sample means is actually the population standard deviation divided by the square root of N. These are on your formula sheet, so if you look under chapter 8, that is the first bullet, the mean and standard deviation for the sample means. All right, and that is the big thing that we are working on the rest of the day today. So let's look at a problem. Everybody have your formulas down? Yeah, I heard you.
What?
You say you were about to fall asleep?
No, that was not me.
Oh,
That was not me.
I heard it. I'm offended.
Can't believe you thought it'd be me.
I was mostly initially.
Weren't you having a Halloween party in there? That's pretty bad. Okay, so let's look at this one. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 and a standard deviation of 0.02. Find the mean and standard deviation of the sampling distribution of 200 simple random samples. Okay, so my mean of my sampling distribution is the same as the mean of the population, which is what?
2.46.
My standard deviation for the sampling distribution is the population standard deviation, which was 0.02, divided by the square root of N, and how many pennies are we talking about? So 0.02 divided by the square root of 200, let's go 4 decimal places, so we get 0.0014. So what if I said we were only looking at 100 samples? What would my mean be? 2.46. Standard deviation would be .002, which kind of corresponds. I told you that the bigger your n, the smaller your standard deviation. In the first one, my n was bigger and my standard deviation was smaller. Okay, so the bigger the n gets, the smaller our standard deviation will be. All right, let's connect this to what we have been doing with our normal distribution. So I told you they were normally distributed. Okay, this is the same scenario. But I want the probability that in a simple random sample of 10 pennies, minted after 1982, we will obtain a sample mean of at least 2.465 grams. All right, so let's kind of write down some information. We know that in my total population, my population mean was 2.46. Population standard deviation is 0.02. My sample, how big of a sample do we have? Our n is 10. So now, in that sample of 10 pennies, I need the probability that the sample mean is at least, so greater than or equal to 2.465. All right, think back to what we have been doing. What do I need to turn that into? A z-score. But I am talking about the x-bar. So if I'm going to turn that into a z, I need the mean and standard deviation for x-bar. So the mean for x-bar is the same as population mean, 2.46. Standard deviation for x-bar is population standard deviation divided by the square root of n. So I'm going to use these to get my z. So z is x minus, since this was x bar, I'm doing the mean for x bar divided by the standard deviation for x bar. So we are finding the probability that the z is greater than or equal to 0.79. How do we do greater than on our table? Okay, so look up 0.79. And the probability there. Okay, so then 1 minus 0.7852 gives us 0.2148. So this is really the same thing we have been doing, but since I'm talking about x bar, when I find my z, I have to use the mean and standard deviation for x bar. That is the only thing that has changed. Any questions on that? Let's practice some more. So the engines made by Ford for speedboats had an average power of 220 horsepower. What is that representing? And a standard deviation of 15. A potential buyer intends to take a sample of 4 engines. So what is that for? And will not place an order if the sample mean is less than 215 horsepower. What is the probability that the buyer will not place an order? So, will not, that means the mean was less than 215. So we have to turn that into a z. But if I'm going to find my z, since my variable is x bar, we need the mean and standard deviation for x bar. So the mean is the same as the original mean. Standard deviation is 15 divided by the square root of 4. 7.5. So now we need our z. Z is x minus the mean divided by the standard deviation. That gives us a negative 0.67. So now, less than, that's what our table tells us. So we go to the table, look up negative 0.67. 0.251. Is that okay? Let's look at another. The IQ of humans is approximately normally distributed. So notice I'm always telling you it's normally distributed, which is what allows me to use my n, or my normal distribution. The mean is 100. Standard deviation is 15. I want to find the probability that a simple random sample of size 10, so that is my n. The sample mean, so find probability that x bar is greater than 110. What is the mean for x bar? Standard deviation for x bar is the population standard deviation divided by the square root of n. I also want to caution you, make sure on that standard deviation you are leaving a few decimal places. If you round that too much, it will throw all of your numbers off. So I try to leave 4 on that. Also, just make sure you're writing down your standard deviation, because if you rounded it to 3 decimal places, you might get a slightly different probability, so I need to know where it comes from. So just make sure you're showing me your work. So our z is our x bar minus the mean divided by standard deviation. So probability that z is greater than, that would be 2.11. How do we do greater than? 1 minus. Look up 2.11. So we get 0.0174. Okay. So let me ask this question. If I looked at the probability distribution for rolling a die, okay, so we know that your possible outcomes when you roll could be a 1, 2, 3, 4, 5, 6. What is the probability of each of those?
1/6.
Is that normally distributed?
No.
No, normally distributed, remember, that means it's a bell shape when you graph it. This would be uniform because everything had the same. So if it's not normally distributed, I can't use my normal distribution to estimate probabilities. But if we took samples, so this case, if I'm taking 200 random samples of size 4 and calculating the mean. So I roll the dice 4 times, find the mean, write that down. And I do this 200 times, so I have 200 means. It actually turns out as you start to graph those, that's what it would look like. So it's fairly normal, isn't it? Okay, the next one is if I roll it 10 times, get the mean. 10 times, get the mean. And I repeat that 200 times. It's even more normal. Or if I roll 30 times and get the mean, it's even more normal. So it turns out as we do this, as our samples get bigger, the sample means will be normal, even if the original data was not. So the key things here, the mean of the sample mean is always the population mean. Standard deviation of the sample mean is the population standard deviation divided by the square root of n. Regardless of the original distribution, the shape becomes normal as n increases. And that's called the central limit theorem. There is actually a name for that. But then what the important question for us is, how big does it have to be before we can say it's normal? So either the original data has to be normal, or it has to be big enough that we can assume it will become normal. And our guideline from here on out, we will use this frequently. If it is 30 or more, the sample mean is approximately normal. So our sample means will become normal as long as we have 30 or more. If we don't have 30, so if n is less than 30, then that means our original population has to be normal. Before we can use that table to read our probabilities. So either the original data has to be normal, or we have to have at least 30. All right. I know I've taught almost the whole class. Are you guys okay with me finishing it? I promise tomorrow's section is much shorter, so you will get class time tomorrow. I just want to do these last 2 examples. And I promise tomorrow will not take me as long. Okay. So suppose the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes. So our actual mean is 11.4. Standard deviation is 3.2. If a random sample of n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. Okay, this is going to become a frequent question. I'm asking you to describe it. Basically, I'm asking you to tell me, is it normal, the mean, and standard deviation? That's all I'm looking for. So, would this one be normal? I didn't tell you it was. But how do I know it will be? Yep. So, n is greater than 30, which means it is normal. The mean for the sample means is the same as the population mean, 11.4. Standard deviation for those, population standard deviation divided by the square root of n. What's my n? 35. So we get 0.5409. So B, what's the probability that the mean time is less than 11 minutes? So what do we have to do? We already found the mean and standard deviation. So 11 minus 11.4 with 0.5409. That's a -0.74. Less than is what our table tells us. we look up a negative 0.74.
0.2297.
Doing okay with these? Should be, hopefully you're getting kind of bored with looking up the normal probabilities, finding the z-score and looking that up. We're doing it over and over and over and over again now. All right, last problem of the day. The mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9. Okay, we have a sample of 35 low-income patients, and we find that their mean weight gain was 36.2. So what is this? That's the mean of my sample here. Okay, does this result suggest anything unusual? So first of all, let's decide, is this normal? Yes, and it's bigger than 30, so it is normal. All right, the mean for my normal distribution, or for my sampling means, would be 30. Standard deviation, 12.9 divided by the square root of 35. Gives me 2.1805. Okay, so to decide if this is unusual, unusual means what? Less than 5%. So we need to find the probability that the average weight, should I find the probability that the average is more or less than this? More. Why? What is the average overall? 30. So wouldn't we expect it to be less than that? So finding the probability that it's less than 36 really isn't going to help me. Let's find the probability that it's more than that. So we need our z. X minus mu over sigma. So the probability that z is more than 2.84. More than, we have to do 1 minus 2.84. So there is only a 0.23% chance of this happening. So is it unusual? Yes. Okay. So what that means is either we have a bad sample for some reason, or the average weight gain for the low-income families is higher than what we expected. So either we have a bad sample, or there's something that makes this sample different than the entire population. Okay, that's 8.1.